It's my great honor to introduce study and practice on performance-based seismic design of Loess engineering in China. The following 6 parts will be involved in my presentation. Part 1, background. Loess covers an area of 640,000 square kilometers in China. 4.9% of the global Loess area. The Loess Plateau is located in the north central of China, which covers 440,000 square kilometers, involving 7 provinces. Loess tablelands, ridges, helix, valleys and terraces are the typical topography of the Loess Plateau. The depth, the thickness of the Loess deposit in the plateau ranges from 10 meters to more than 500 meters formed in quaternary. Due to its gradation and porous microstructure, Loess have a high dynamic vulnerability and high collapsibility and the effect of earthquakes and waters. In history, many great earthquakes and strong earthquakes occurred in the plateau, caused 1.4 million people died. Seismic fortification acceleration ranges from 0.1 to 0.4 G in most range of the plateau. This table shows the death toll caused by devastating earthquakes in Loess Plateau. Except poor performance of local houses, site effect landslides, liquefaction, and seismic subsidence is a main cause for huge death toll. Earthquake intensity on the top of the Loess mountain were amplified by 1 to 2 degrees at least for the Wenchuan 8.0 earthquake. The damaged high-rise building and chimney and many infrastructures away hundreds kilometers away from the epicenter was attributed to predominant slow attenuation and amplification of thick Loess deposit site on ground motion during the Wenchuan earthquake. More than 7,000 Loess landslides were induced by Haiyuan 8.5 earthquake in 1920, which caused 1/3 of the death toll. Some liquefaction triggered large-scale sliding flows in Loess deposit were induced during strong earthquake. Remarkable subsidence of 1 to 4 meters on Loess sites were caused by greater earthquake. Part 2, attenuation law and site effect of strong ground motion. Based on as seismo maps of 7 typical greater earthquakes in the Loess Plateau, we figure out the attenuation equations for elliptic shape with a long axis and a short axis respectively. And then we added 23 selected earthquakes with a magnitude of 5 to 8.5 in the plateau to figure out the attenuation curves of seismic intensity versus seismic versus distance away from epicenter. The two figures shows law for long axis and short axis elliptic shape. Based on the thousands of ground motion recordings, we figure out the attenuation curves of PGA with epicentral distance. This formula can be used for estimate the attenuation of PGA in the plateau. Based on field investigation and a large number of shaking table tests, the amplification coefficient of PGA with a different thickness of Loess site were proposed for different fortification seismic zone. And also characteristics periods adjusted with different thickness of Loess deposit proposed in this table for different seismic acceleration. For Loess slopes, amplification factors can be adjusted according to the table with a different slope angle and different heights. Comparison between Loess site effect and the general site effect in the current Chinese seismic design code shows that with the fortification PGA less than 0.2, the amplification factors greater than general site effect. And also characteristic period is longer than all of kinds of site. Part 3, seismic design of engineering slopes of Loess. We classified the engineering site into 4 types: favorable, general, unfavorable, and dangerous sites, respectively corresponding to stable of slopes, slight landslides, moderate landslides, serious landslides. Many buildings are constructed at the foot, crest, and half up the slopes in the Loess plateau. So we proposed safety factors of Loess slopes in specification for seismic design of buildings in Gansu province. 1.2 for seismic condition, 1.2 for rainfall condition, and 1.35 for normal condition. For building slopes with the height of 10 to 50 meters apart from the seismic stability of a slope or a reinforced slope meeting the requirements of safety factor, the building slope should meet the following 5 specifications. Otherwise, the building slope should be carried out a special study. Specification 1. When the high-rise building is located at the slope crest, the distance between the building and the edge of the slope crest, and the distance between the edge of the foundation slab and the edge of the slope bottom should be limited to the design value shown as the red check mark. When the multi-story building is located at the crest of the slope, the same two distance should be limited to the design value shown as the two red check marks. When multi-story and high-rise buildings are located at the slope bottom, the distance between the buildings and the edge of the slope bottom should be controlled within 10 meters. When the high-rise building is located on the platform in the middle of the slope, 5 design values should be followed, shown as the figure. When the high-rise building is located on the platform in the middle of the slope, also the 5 design values should be followed, shown as the figure. For liquefaction-induced Loess landslides, 2 of key factors should be considered. One is a set effect, and the other is the effect of water. Water can be come from underground rainfall, irrigation, and drainage. The water can saturate the Loess deposit, triggering liquefaction, develop sliding surface, and decrease the dynamic strength of the soil deposit, which has been mentioned by Professor Jonathan Bray yesterday. For matching fortification target of the buildings, which is no collapsing and rare ground motion, the risk assessment for landslides should be adopted with exceedance probability of 2% in 50 years. A serious shaking table test were performed to investigating the mechanism of liquefaction-induced landslides. 2 of cases for saturation locations were considered. One is the saturation layer is located at the bottom of the slope model, and the other located on the surface layer of the model. The test results show that failure model of the slopes have a close relationship with the development of pore pressure and amplification of acceleration. And also, test result show that mud flow can be triggered on the saturated surface layer of the slope, which which have a close relationship with development of pore pressure increasing. The safety factor of Loess slopes and the coupling effect of earthquake and water can be estimated with the following formula and two curves and corresponding formulas. For saturated surface soil layer and unsaturated soil deposit with a high water content. Part 4, evaluation of liquefaction and its seismic design. We classify the engineering site into 4 types according to a liquefaction potential. No potential, slight potential, moderate potential, and serious potential. The site table is also favorable site, general site, unfavorable site, dangerous site for seismic design. The preliminary discrimination method were proposed for liquefaction of Loess ground, which involves in age of the deposit, soil deposit, saturation of the Loess ground, clay particles, and the thickness of non-liquefiable soil layer and the depth of groundwater level. Large number of SPT tests for saturated Loess site were performed on site. Based on the test results, the detailed discrimination method for liquefaction of Loess ground were proposed with following formula, which can be used for a Loess ground within 20 meters depth. The reference value of SPT counts N0 can be selected from the this table. We can see that the value of the reference counts is lower than saturated sand and silt. And also we can calculate the liquefaction index with the following formula based on the SPT counts. The detailed discrimination of liquefaction also can be carried out based on dynamic triaxial tests or torsional tests with following 2 formulas. A large number of liquefaction treatment tests were performed on site. The results show that dynamic compaction treatment and compaction pulse treatment can obviously reduce seismic potential of liquefaction. Chemical grouting treatment can completely eliminate the potential of liquefaction. Also, some improved treatment such as lignin can obviously reduce potential of liquefaction. So performance-based seismic design standards for saturated Loess grounds against liquefaction were proposed in this table. The key factors is compaction coefficient, which ranges from 0.9 to 0.995. Performance-based seismic design method of improving Loess ground with linking is proposed in this table for different fortification design acceleration zone. Piles foundation also can be used against liquefaction of Loess ground, but seismic design for pile foundation should check the stability before the earthquake, and after liquefaction, according to this standard. Treatment standard for liquefaction of Loess ground is listed in this table with a different degree of liquefaction for different class of buildings. Part 5, evaluation of seismic subsidence and its seismic design. For seismic subsidence evaluation, we also classify the engineering site into 4 types: favorable, general, unfavorable, dangerous sites, corresponding to non-subsidence, slight subsidence, moderate subsidence, and serious subsidence, respectively. A large number of test results carried out for seismic subsidence of Loess ground. Based on the test, the method of preliminary judgment on seismic subsidence of Loess ground were proposed in this table, which involves the age of Loess deposit, microstructure type, water content, void ratio, dry density, compaction coefficient, as well as the other indexes listed in the table. The detailed discrimination of seismic subsidence of Loess grounds is proposed with this formula and 2 tables. The up table is for a Loess ground of buildings. The lower table for Loess ground of underground structures. The treatment standard of seismic subsidence of Loess ground is proposed in this table with different seismic subsidence grade, slight, medium, serious, for different level of buildings. The verification field test show that dynamic compaction can make seismic subsidence coefficient of Loess within 6 meters less than 1%, and the seismic action of 7 to 8 earthquake degree, intensity degree. The design criterions for piles foundation against seismic subsidence before and after the earthquake is proposed, shown as 2 figures. Last part, seismic design and treatment of Loess embankment for high-speed railway. The planning network of National Rapid Railways of China is shown in this map. Based on the plan, 8 vertical and 8 horizontal high-speed railways will be completely constructed in 2030, which will be 45,000 kilometers long and connect all provincial capital cities and other large and middle cities with a population of over 500,000. But 8 railways cross the Loess Plateau region. Zhengzhou to Xi'an high-speed railway is one of them, which is more than 400 kilometers long, connecting the 2 capital cities of Henan province and Shanxi province. It was constructed in 2005 to 2009 and begins to operate in 2010. The railway crosses the southeast part of the plateau, where the thickness of Loess deposit ranges from several meters to 10 meters. 65% of embankment and subgrade have collapsibility and seismic subsidence. Some sections have liquefaction potential, which is a major challenges for the seismic design of the railway. The deformation of embankment is composed of the 4 respects. The third one, subgrade deformations due to collapsibility, seismic subsidence, and liquefaction is a major challenge. So before the design of a railway, we have no, there is no code, design code to follow. The field tests were performed for evaluate collapsibility of Loess ground along the railway. The test result shows accumulated settlement versus depths of Loess deposit. Collapsible types and the grade of Loess site along the railway is listed in this table. The collapsible grade ranges from 2 to 4, the highest level. Seismic subsidence of Loess grounds and rare ground motion is 16 centimeters. Liquefaction of Loess grounds and fortification and rare ground motions may be triggered. So comprehensive treatment against collapsibility, seismic subsidence, and the liquefaction of Loess grounds along the railway was considered based on the field test. The standards treated by piles, thrusted, expanded with column hammers is proposed in this table. The key factors, key index is average compaction coefficient, which is ranges from 0.93 to 0.97. This table shows the standard treated by cement compaction piles. Also, the key factors is similar to the above mentioned value. This table shows the standard treated by dynamic compaction, which was used in Loess site less than 6 meters deep. The treatment by improved Loess environment were implemented with the standard listed in this table. The compaction coefficient ranges from 0.92 to 0.95. Certification of treatment efficiency were carried out based on immersion tests on engineering site. The observed data show that after immersion of 87 days, compression settlement for 3 kinds of reinforced grounds are reduced within the standard 0.015. As 4 figures shows the test results. Finally, the standard were posted in this table for treatment, seismic treatment of pile, serrated, expanded column hammer, and cement compaction pile. Average compaction coefficient was adopted with 0.92, 0.93. So improved Loess embankment plus reinforced Loess ground can keep total deformation within 50 millimeter. Conclusions. The first, slow attenuation law and the amplification effect of Loess sites on ground motion should be considered in the determination of seismic design parameters. The second, performance-based design of engineering slope, Loess slopes may consider the 3 conditions together: earthquake, rainfall, and normalcy. The last, performance-based seismic design for Loess grounds and embankments can be implemented by comprehensive evaluations and treatments against liquefaction, seismic subsidence, and collapsibility together. Thank you very much for your attention.
Thank you, Professor Wang, for your detailed and excellent presentation on this Loess soil and related hazards in the earthquake engineering. starting from liquefaction, then improvement of ground, piles, etc. So I guess we are running out of time, but I would like to take one or two quick questions if anyone is having for Professor Wang. Please ask, or even you can write in the question answer session or the chat session, which is open. We can quickly take one or two quick questions.
Thank you.
So, Professor Wang, I can see that there are two queries mentioned in the question answer session. One attendee is writing, thank you for interesting presentation. For those they are not familiar with Loess, could you please explain what is the special point about it? Are they the plastic, non-plastic, organic, crushable, or porous? What kind of soil is it?
You mean plastic deformation?
They're asking about the soil classification, the Loess. As
Yes.
we understand, it is airborne. So they're asking what type of soil. Is it plastic or non-plastic?
Plastic, plastic soil. It is a typical plastic soil with porous microstructure. So they have enough basis for collapse of structure and the effect of earthquake and effect of water.
Yeah, thank you. The second question in the session, someone asked one attendee that what about the retrofitting? That is the existing structures or the current structures on this Loess soil with as per the new standard, what you have mentioned, how those existing structures are getting retrofitted, or what way the new treatment has been imposed on those existing structures.
So generally speaking, all kinds of techniques of ground treatment can be used for Loess grounds. But some of them have more efficiency to eliminate collapsibility of Loess, and some of them have a more efficiency for seismic subsidence and liquefaction. For example, chemical grouting treatment is very efficient for against liquefaction potential. And dynamic compaction and piles, compaction piles foundation can obviously reduce seismic subsidence of Loess ground, but have less efficiency for liquefaction potential. And also dynamic compaction is efficient for shallow Loess grounds within 6 meters, but it cannot be used for a very thick Loess deposit. The piles foundation can be used for very thick Loess deposit. It can cross the soil layer with liquefaction potential and seismic subsidence potential and collapsing ability and the effect of water. So it depends the cost and efficiency of the techniques.
Thank you,
you.
Professor Wang. We appreciate your answers and nice presentation. We show our appreciation in the form of our regular practice.
Thank you.
And
Thank you.
With this, we close this keynote session. I know we are running out of time, and I thank Professor Russell Green. Professor Green, you can summarize further and say the closing remarks, and thank both the keynote speaker, Professor Susumu Yasuda, as well as Professor Lanmin Wang. And thanks to the organizers.
Yeah, thank you very much to
Thank
both
you.
of the speakers. Excellent presentations. And we will call this session to a close.
Yeah.
Thank you.
Thank you. Bye.
Thank you.
Thank you. Bye.
Dipankar
Thank you,
and,
everyone.
Russell and everyone.
Bye.